Okay, so we're doing a calorimeter problem. In specific, this is a calorimeter problem where we're having a hot piece of metal thrown into a cooler water inside an insulated calorimeter. So whenever you do these problems, there's going to be a certain equation you want to follow, and it starts with the first law of thermodynamics that says that the total energy change for any isolated system has to equal 0. So our calorimeter is insulated, which means that no energy is going in or going out. So the change of energy is 0. So what does this mean? Well, this means that whatever energy is lost by the metal has to be gained by the water. So in equation form, this would be Q lost plus Q gained equals 0. So this just means whatever energy is lost by the hot metal is going to be gained by the water inside the calorimeter. And the total change is 0 because it's insulated, no energy is going in or out. So the next step for these problems is you want to subtract one of these to the other side of the equation. And it really doesn't matter which one. So we'll just move the Q gained to the other side. So this equation becomes Q lost equals negative Q gained. Well, what energy is, which one is losing energy? Well, it's going to be the metal block. So the metal block is going to be cooling down, so it's losing energy to the water. So this side of the equation is going to be for the metal, and then the right side of the equation is going to be the water. So the energy, or the water, is going to gain whatever energy the metal loses. Well, what do we know that Q is equal to? Well, we know Q is equal to mc delta T. mc delta T, and we're going to write delta T as temperature final minus temperature initial. So this is what we've been studying in chapter 5. So mc delta T, and then on the right side we can also write this as mc delta T. So mc temperature final minus temperature initial. Now just be careful, you need to keep this negative sign on this side. And it actually really doesn't matter if you want to keep the negative sign on the left side, that's fine. The negatives are going to cancel out at the end anyways. So this is an equation that's important. Whenever you see a calorimeter problem that is a hot metal being thrown into water, this is the equation you want to use. So I would remember this. This is an important equation. All right, so now we got it set up. Let's plug in some values. So for the metal side, the M stands for the mass of the metal. So in our problem, we're told that the mass is a 25-gram copper block. So the mass is 25. The C stands for specific heat, which you'll have to be given. So 0.250 or 0.250. Temperature final, well, that's what we're looking for in the problem, so we're going to leave that as a variable. And then initial temperature, so we're told the copper metal is heated to 375 degrees, so minus 375. Okay, and that's equal to, and now keep the negative sign here, negative. Now the mass on this side is going to be the mass of the water, so we're told this calorimeter has 405 grams of water. The specific heat value, which your teacher may or may not give in this course, is not given, you're expected to memorize, but just check with your TA or your professor. The specific heat of water is 4.184. And then the temperature final, which is also unknown, that's what we're searching for, minus the initial temperature of the water, which is 22.1 degrees Celsius. All right, so now we got our problem set up, and from here it's essentially just a algebra problem. Now you might be wondering, well, we have one equation, but there's two unknowns. We have temperature final for the water and temperature final for the metal. So how do you solve that equation? Well, the key here is the word thermal equilibrium. So thermal equilibrium means that the final temperatures of all objects in the calorimeter are the same. So the temperature final for the metal is actually the same as the temperature final for the water. So it is just one equation with one unknown. And I have answer key here, I think. All right. So from here, it's going to be an algebra problem where you're practicing your foiling. So we're going to distribute this into this one here. So multiply those, and then we're going to multiply these two here. So the 25 times 0.250, excuse me, so that'd be 6.25. And then we're keeping the temperature final minus the temperature initial, 375. And this side multiplying 405 times 4.184. So that's minus 1694.5. And still temperature final minus temperature initial of the water. And from here we're going to FOIL again, or distribute rather. So multiply those two into each other. And here we're going to multiply those in. So this we're going to get 6.25 times temperature final, and 6.25 times 375 will give you minus 2343.75. And on the right side we'll get, make sure I'm still on the screen here. Oops, okay. So on the right side, when we distribute this, we're going to get minus 1694.5 temperature final, minus, and notice this is going to be a minus times a minus, so this becomes positive. So plus 3,700, well, so let's see, 37,448.9. And from here, what we're going to do is combine like terms. So on the left side, we have some temperature finals, and the right side, we have temperature finals. So those are going to be combined, and then we also just have numbers, so those are going to be combined together. So again, this problem is really just a large algebra problem, and it's really easy to make mistakes leaving negatives out or combining in the wrong order. So if you do it correctly, you should get 1,700.75 temperature finals is equal to 3,970, well, let's see, 39,792.6. So now we have temperature finals on one side and just the numbers on the other side. And so you're going to divide both sides by 1,700 to get temperature final for both the water and the metal to be 23.4 degrees Celsius. So that's your final answer for the problem. This is the final temperature of the metal and the water since they're equal. And a good way to check is your final temperature has to be in between the two original temperatures. So the original temperature of the water was 22.1. and the original temperature of the metal is 375. Our answer falls in between that, so we have relatively confident that we have the correct answer. So, all right, hope that helped.